Dear students, I welcome you all to this tele-learning session of physics focused on a new chapter, probably the last chapter in physics, your communication system. So, in a broad sense or in a simple way, I can say that what do you mean by communication system and what we are going to learn in this chapter. Basically, I can say that think of a person is singing in a studio. Now, you are listening this same in your television screen. I am delivering this program here and you are observing the same in your television screen. Now, what is the entire process involved in this thing? We are going to discuss in detail that how this entire process starting from the recording from here to the deliberation at your screen is going on in this process. Now, before going into that, we must concentrate upon certain aspects of a communication system, like one thing is modulation and other one is the radio wave propagation. These two things we have to concentrate upon before going into your communication system, before going into the concept of transmitting section and receiving section. Now, what is modulation? Say we can say that modulation, what do you mean by modulation? We can say that modulation is a process in which the signal wave is superimposed on a high frequency carrier wave. Now, question is what is the necessity of that? I am just giving you a simple analogy. Say you are residing at your home during this period and in this afternoon let you want to have an ice cream. So, you asked your brother that go and fetch an ice cream for me from the market. Your brother, since he has no other communication vehicle, he walked to the market, brought that ice cream and returned back to home. But when he has brought that ice cream, you started to cry. Why? Because it has already melted. Now, your brother has again gone to the market. By this time, he has brought the ice cream by a bicycle. Again it is not in good condition. Now, the third time he has gone to the market and brought the same ice cream by means of a bike and it has now brought in a good condition. Think of the difference. In this case the ice cream is same, the place from where it is brought is same, the distance that your brother has covered for bringing that ice cream is the same. But what is the difference? Difference is the carrier that your brother have used to bring that ice cream to home is different. And depending upon the nature of carrier that you are using, the quality of ice cream that he has bought is different. Similarly, when we are speaking, this signal wave cannot travel a very long distance because our earth is a good conductor. So, upon covering a very small distance, it will get absorbed by earth. So, it has to be sent through a high frequency carrier wave and by telling high frequency carrier wave, that means either I have to use the radio wave or microwave, and why I will use radio wave and microwave, that I will discuss later. So, now comes the what is the necessity of modulation. First point is audio and video signal over a range of frequencies, cover a range of frequencies. So, even if transmission is made possible, no receiver can be tuned to them. And what do we mean by that? When I am speaking, different part of my voltage or voice is at a different frequency level. So, a transmitter cannot send all these frequencies at once. That means what? If it sends some frequency, it will cut out some other frequency. So, there will be a distortion in the signal. Second point is, if however, the transmitter is able to send the signal and the receiver receives the signal, but different radio stations are broadcasting signals at the same frequency. So, there will be overlapping of signal of different radio stations. Come to the third point. To transmit signal at audio frequency range, an antenna of very big size is required, and the fourth one is the radiation efficiency at a low frequency is poor. And due to all these parameters, due to all these limitations, modulation is required. Now, come to what is modulation? The phenomenon by virtue of which the amplitude or frequency or phase of a RF carrier wave is changed in accordance with the instantaneous intensity of the modulating signal is called your modulation. In modulation, what occurs? A carrier wave which is in general in RF frequency, radio frequency range, and a modulating signal means say the voice signal, I can say which is in audio frequency range are mixed such that we get a modulated signal, and this modulated signal again in radio frequency range. So, this process is called your modulation. Now, since there are 3 parameters that can change, accordingly modulations are basically of 3 types. 1. Amplitude modulation, 2. Frequency modulation, and the third one is phase modulation. Now, first comes to amplitude modulation. This is a type of modulation in which the amplitude of the carrier wave changes in accordance with the signal intensity, while the frequency and phase remains constant. Now, how this thing occur? Suppose this is a signal wave here and this is say your high frequency carrier wave. This has got a frequency Fs, this has got a frequency Fc. When this signal wave is intermixed with your carrier wave, say this is point O, this is point A, from O to A the intensity increases. So, we can say the amplitude of the carrier wave accordingly increases, and again when it decreases intensity, then it again decreases. So, we will get a modulating signal like this. So, this modulating signal again at a frequency Fc, but it consists of 3 frequency components. 1, this is an upper sideband having a frequency Fc plus Fs, and this is a lower sideband having a frequency Fc minus Fs, and this wave propagates with a frequency Fc. So, the amplitude modulated wave consists of 3 frequency components. One is Fc, other one is Fc plus Fs, and the third one is Fc minus Fs. Accordingly, we can say the bandwidth for transmission of this amplitude modulated wave is frequency of upper sideband minus frequency of lower sideband, and that equal to your Fc plus Fs minus Fc minus Fs, and this equal to implies your bandwidth of transmission is your 2Fs. So, the bandwidth of transmission comes out to be 2Fs. And if another interesting fact is that if in a locality there are 2 AM radio stations, the frequency difference between them should be at least 9 kilohertz. That means what? That means if some radio station uses a frequency F, then the other radio station in that locality must use a frequency Fc plus 9 kilohertz. Now, come to the analysis of this amplitude modulation. Let us discuss or let us analyze this amplitude modulation. For that reason, I can say that in amplitude modulation what happens, that the amplitude of the carrier wave changes in accordance with the signal intensity. Let your EC equal to capital EC cos omega ct plus phi. Phi is the initial phase here. I can put this as phi 0, and ES equal to capital ES cos omega st, where omega c very greater than omega s, that implies Fc very greater than your Fs. Now, let us find out that since phase has no role to play, small ec equal to capital EC cos omega ct plus cos omega ct. Now, amplitude modulation says that the change in amplitude of a carrier wave is proportional to Es. So, I can write that this delta Ec equal to some constant Ka Es. That implies I can write this delta Ec equal to Ka Es cos omega st. So, the modulated wave equation becomes, this is Ec plus delta Ec cos omega ct. So, this becomes something equal to Ec plus Ka Es cos omega st into cos omega ct. So, this becomes equal to, if Ec is taken common, then 1 plus Ka Es by Ec cos omega st into cos omega ct, and this comes out to be Em equal to Ec cos omega ct plus Ma Ec by 2 cos omega s plus omega ct plus Ma Ec by 2 cos omega c minus omega s into t. This equation clearly suggests that there are the 3 frequencies here. One is omega c, other one is omega c plus omega s, and the third one is omega c minus omega s. So, this one is for your the carrier wave, this is for upper side band, and this is for your lower side band. So, this is how your amplitude modulation is carried out, and from this we have come across a term, that term is your Ma. This Ma is your Ka Es by Ec, which is called amplitude modulation index. Amplitude modulation index. This amplitude modulation index, its significance is that its value tells us the quality of the signal superimposed upon the carrier. Now, if the amplitude modulation index has got a greater value, the stronger and clearer will be the signal superimposed upon it. The limiting values of this amplitude modulation index is your 0 and 1. The greater the value of amplitude modulation index, the stronger and clearer will be the signal superimposed upon it. Secondly, the maximum possible modulation without distortion occurs if MA equal to 1 or 100%, and if the value of MA exceeds 1, then over modulation occurs, which causes distortion. And what do we mean by distortion? Distortion means that the input signal and the output signal are not alike. Now, let us discuss what are the limitations of amplitude modulation. The limitations of amplitude modulation are: it gives a noisy reception, the efficiency is low, it has poor audio fidelity, and there exists interchannel and co-channel interference. That means, upon one channel, superimposed upon one channel, there will be other channel can be heard. So, these are the limitations of amplitude modulation index. We have discussed so far what is modulation, the necessity of modulation, what is amplitude modulation and amplitude modulation index, and what is the significance of amplitude modulation index. Now, let us now go to another type of modulation, that is your frequency modulation. In frequency modulation, what occurs, that the frequency of the carrier wave changes in accordance with the signal intensity, keeping your amplitude and phase of the carrier wave constant. Here what happens, if this is the signal wave and this is the high frequency carrier wave, then what happens here, it is Fs and this is Fc, then we will get a modulated wave like this, that as intensity increases, this frequency also increases, then it gradually again decreases. So, this is a frequency modulated wave. In frequency modulated wave, there are several side bands. We have studied earlier that in amplitude modulation index, there are only two side bands, one upper side band, one lower side band. But in case of frequency modulation, the frequency modulated wave has got infinite number of side bands, but out of that only 10 upper and lower side bands are significant. So, we can say the bandwidth here beta equal to f US upper side band 10th number minus f lower side band 10th number. So, I can write this as Fc plus 10 Fs minus Fc minus 10 Fs. So, this bandwidth of transmission of FM wave come out to be your 20 Fs. In a case of amplitude modulation, it was 2 Fs. Now, see the significance here. In case of the bandwidth of transmission for FM wave is larger as compared to amplitude modulation index. And secondly, in the same locality, if there are two FM radio stations, the minimum frequency separation between them should be 200 kilohertz. And in case of amplitude modulation, it was 9 kilohertz. And what does this signify? That there is a less probability of superimpose of different FM radio stations of the same locality, because of this large frequency separation that two FM radio stations are using. Now, let us come to what is frequency modulation index. Frequency modulation index MF equal to the ratio of maximum deviation in frequency to the frequency of signal wave. That shows your frequency modulation index inversely proportional to signal frequency. And what it suggests? That the value of MF decreases on increasing signal intensity. That means, as the signal intensity changes, the value of frequency modulation index gradually changes, and as Fs increases, this MF value gradually decreases. Now, unlike your amplitude modulation index, this the value of MF is not limited to 1, but in case of amplitude modulation, the value lies between 0 and 1, and if it exceeds 1, MA exceeds 1, then over modulation occurs, but there is no such limitation in case of frequency modulation. So, what are the advantages of frequency modulation over your amplitude modulation? It gives noiseless reception. Now, what is noise in electronics? Any unwanted signal is called a noise. Suppose I am speaking and in between the fan is moving and the sound of fan comes to the microphone, then that is also a noise. So, any unwanted signal is called a noise. So, it gives noiseless reception. Second thing is the operating range is quite large. Why? Because due to infinite number of sidebands, the bandwidth available will be large. Then it has high audio fidelity in reception. That means the quality of signal that we get is better as compared to your amplitude modulation. The coefficient of transmission is very high, and the last one is interchannel and co-channel interference are highly reduced. Why it is that? Because in the same locality, when there are two FM radio stations, the minimum separation between the carrier frequency they uses is 200 kilohertz. Due to this reason, there is a less probability that two different channels may superimpose upon each other. With this, then we come to the third and the last type of modulation, that is phase modulation. So, this is a type of modulation in which the phase of the RF carrier wave changes in accordance with the signal intensity, keeping amplitude and phase constant. Here what happens when the signal intensity increases, the phase of the carrier wave changes as per signal intensity. Now, with this we must come to the demodulation process. What is demodulation? This is the reverse process of modulation. That means, retrieving the audio video signal from the modulated wave is called demodulation. We know so far as that during transmission of wave, a RF carrier wave is mixed with the signal wave, and when we reach at the receiving point, then that is again that RF modulated wave, and if we will feed this RF modulated wave directly to the loudspeaker, then the loudspeaker or it cannot generate sound. Why? Because the audible range is 20 hertz to 20 kilohertz, but the RF wave is from range 30 kilohertz to 300 gigahertz. So, if this carrier wave, this RF carrier wave is directly fed to your loudspeaker, then the loudspeaker will not generate any sound. So, it is first necessary to separate this audio signal or video signal from the high frequency carrier wave, and that process of separation of carrier wave or signal wave from the carrier wave is called your demodulation. Generally, demodulation is carried out in a detector circuit. This detector circuit or demodulation of a signal involves two necessary steps. In first step, it rectifies the modulated wave, that is, the negative half of the modulated wave is eliminated, and secondly, it separates the audio signal from the carrier wave, and secondly, it separates the audio signal from the carrier wave. So, the first part rectifies the AM input wave, that means there is a rectifier circuit, and for that rectifier circuit we use generally a crystal diode, and secondly there is an RC filter which filters this RF carrier wave. So, what we observe here, that there is a PN junction which acts as the rectifier here, then here there is a capacitor, and here there is a resistor. So, what we will get here? Here there is the AM wave, and at this point we will get one half cycle is eliminated. So, this will come like this, and after RC filter I will get only the audio signal, and when this audio signal will be fed to the loudspeaker, the original sound will be recreated at the receiving point. So, it basically involves two steps. Here there is your RF modulated wave, which when fed to a rectifier circuit, the lower half of the signal is eliminated, and secondly it is now fed to an RC filter. The value of the time constant of this circuit is so chosen that it separates the high frequency carrier wave from the usual signal wave. So, this is the process how demodulation of this RF modulated signal is carried out. Now, come to a next interesting thing, that what is communication channel? The physical path between transmitter and receiver is known as your communication channel, and this communication channel, we can say that in a communication channel, the bandwidth of communication channel is nothing but it is the difference between the highest and lowest frequency that the channel allows to pass through it is known as the bandwidth of communication channel. Again I am saying the physical path between transmitter and the receiver is communication channel, and the highest and lowest frequency, that difference in frequency that the channel allows is called the bandwidth of communication channel or pass band. Let us now discuss that how your radio wave signal or the signal from a transmitter is communicated or transmitted to the receiving point, or let us now discuss how the signal sent by a transmitter is received by or how it communicates to the receiving point. For that thing we should learn about the space communication. In radio wave propagation it uses different frequency spectrums starting from your 30 kilohertz to 300 gigahertz, and in that frequency spectrum there are several frequency bands starting from your lower frequency band, medium frequency band, high frequency, then a very high frequency, ultra high frequency and extremely high frequency band. And basically these radio waves are propagated by three different means. One, ground wave propagation, second, sky wave propagation, and the third one is your space wave propagation. In ground wave propagation, what occurs that say this is your earth, this is the transmitting station here and this is the receiving station here, and signal directly goes from this to this following the curvature of earth. So, in a ground wave propagation, the transmission from the transmitting section to receiving station occurs following the curvature of earth. Here diffraction of the wave causes the wave to propagate along the surface of earth. The dominant mode of propagation of frequencies is below 200 megahertz. That means, it is suitable for transmission of frequencies below 2 megahertz, because if the frequency exceeds 2 megahertz, then due to good conducting nature of earth, it gets absorbed by the earth or it gets attenuated very quickly. This propagation is used in AM radio broadcasting, and another interesting factor is that this type of broadcasting, this type of propagation is not affected by adverse atmospheric conditions. Due to this reason, the emergency radio frequency in every nation is in ground frequency mode or in through ground wave propagation. Then comes your sky wave propagation. In the sky wave propagation, what occurs that a radio wave, this is your earth and this is your ionosphere. So, here what occurs that from a point, transmitting point, a radio wave is sent and from one of the layer of ionosphere it returns back to the receiving point. This is called skywave propagation. So, a radio wave directed towards the sky and reflected by the ionosphere towards the desired location of earth is called skywave, and such type of propagation is called skywave propagation or ionospheric propagation. A radio wave of a frequency between 2 megahertz to 30 megahertz can be reflected by the ionosphere, and if the frequency exceeds 30 megahertz, then it will penetrate the ionosphere and will escape beyond the it will never return back to earth. Now, let us discuss that how ionosphere helps in skywave propagation. Ionosphere is a weakly ionized medium. Due to intense sun rays, it is highly ionized. So, the speed of radio waves is more compared to the unionized air. Thus, ionosphere behaves as a refracting medium whose refractive index is slightly less than 1, and this refractive index is given by small n equal to 1 minus 81 n by your f square, where f is the frequency of a radio wave, and this n is your electron density, Now, what happens here, as the signal from transmitting station gradually enters into ionosphere, it gradually bends and bends away from the normal, and from a particular layer it is incident with critical angle and it again returns back to earth. That means, the total internal reflection, the principle of total internal reflection is used to return the sky wave from a particular layer of ionosphere. Now, come to the critical frequency. The critical frequency for any ionospheric layer is the highest frequency that is returned from that particular layer on vertical incidence, and since it returns back to earth, we can say that this n equal to 0 and f is your critical frequency f c. So, I can write that 1 minus 81 n by f c square equal to 0. This comes out to be f c square equal to 81 n. That implies your f c equal to 9 square root of n. This is the expression for critical frequency for any ionospheric layer, where capital N is the electron density of that particular layer. Ionosphere has got 4 layers D, E, F1 and F2, and in the night this F1 and F2 layer merge to give a single F layer, and the critical frequency of this highest F layer is 10 megahertz. That does not mean that beyond 10 megahertz it will escape into the outer space, because transmitters generally send radio waves obliquely on ionosphere. That means, generally radio waves from transmitter reaches or falls on ionosphere obliquely. Due to that reason, the highest frequency that is returned back by any particular ionospheric layer is greater than the critical frequency and is denoted by f max, and this maximum frequency can be given by a law called second law, where f max equal to your f c sec phi, where f c is your critical frequency and phi is the angle of incidence. Now, for vertical incidence, phi equal to 0 degree. So, f max equal to f c. That means that this maximum frequency will be same as critical frequency only for vertical incidence, and for any other oblique incidence it is greater than critical frequency. That means, the highest frequency returned by the ionosphere is about 30 megahertz. Now, if the value exceeds this 30 megahertz, then it will escape into the ionosphere, and for that reason your satellite communication is required. That means, if the frequency of the radio wave exceeds 30 megahertz, then we can say that this satellite communication is used, where we can say there is a satellite here, it can act as an antenna placed at a very high, then here the ray goes, it processed here and again returns back to earth. So, for communication of radio waves beyond 30 megahertz, satellite communication is required. And apart from this, there is one other type of propagation, that is called space wave propagation. So, in space wave propagation, what occurs? This is a transmitting antenna, this is a receiving antenna. Here one ray goes, this is called a direct wave, and there is another wave, this is a ground reflected wave, and these two waves reach this receiving station in phase. So, the strength of the signal will be high if both these waves reach the receiving station in a same phase, and if they reach there out of phase, then the strength will be weak. So, in this type of propagation, radio wave travels in lower few miles of Earth's atmosphere. It includes a direct and a ground reflected wave, and sometimes it is known as direct line of sight communication. Here the strength of the signal at the receiving antenna depends on two parameters. One, distance between these two antennas, and the second thing is whether direct and ground reflected wave are in phase or out of phase. Suppose they are out of phase, then the height of the receiving antenna can be increased or decreased to make these two waves reach there in phase. And to enhance the strength of the signal by enhancing the height of the receiving antenna is called your selective fading. So, up to 2 megahertz of radio wave transmission, ground wave is effective. So, what we have discussed so far, that for radio wave propagation or transmission up to 2 megahertz, ground wave propagation is extremely good. Then from your 2 megahertz to 30 megahertz, the skywave propagation is useful, and beyond 30 megahertz, communication in the range exceeding 30 megahertz, that is in a very high frequency range or ultra high frequency range or in microwave range, space wave propagation is established using satellites. Cellular phones operating in a microwave range uses space wave propagation. So, we can say that this space wave propagation is meant for, or satellite communication is only meant for communication beyond 30 megahertz. Now, with this idea of modulation and with the idea of your radio wave communication, now we are in a position to discuss how a simple transmitter section works and how a simple receiver section works. Now, first come to a transmitter section. Now, in transmitter section, what occurs, that this is a microphone here, this is a microphone. When somebody speaks in front of the microphone or in front of a video camera, it is converted into corresponding audio frequency signal or audio frequency AC. This audio frequency AC is now fed to an AF amplifier. This AF amplifier enhances the strength of the signal. This signal is now fed to a mixer or modulator. This is say a mixer, or we can say this as a modulator. This frequency is in Fs. This is your audio frequency Fs. There is a local oscillator here which generates the desired RF carrier AC or carrier wave of a frequency FC. So, what we will get here? We will get an modulated wave. And it is otherwise called an RF AC, whose frequency is FC, same as carrier frequency. This is now fed to a RF voltage amplifier, where voltage level of the signal is enhanced. And you can say there are several stages of voltage amplifiers. Basically, there are 2 or more stages of voltage amplifier to enhance this signal. Then this is now fed to one RF power amplifier, where power level of the signal is enhanced. Now, this is now fed to an antenna. This is your transmitting antenna, which sends this modulated signal into the space. So, what we observe here, this is your sound wave. That means a singer sings in front of a microphone. This microphone converts this audio signal into corresponding or converts this sound wave into corresponding audio frequency signal. This AF amplifier enhances the strength of the signal, and this AFFC is at a frequency Fs. Here it is fed to a mixer or modulator. The mixer and modulator gets another input from a local oscillator, which generates your RF carrier wave. Now, this RF carrier wave has got a frequency Fc. This modulator intermixes both this thing, or the signal wave is superimposed upon the carrier wave, and the resultant radio frequency modulated wave or RF wave is now fed to a RF voltage amplifier to enhance the voltage level of the signal. Now, there are several stages of voltage amplification to enhance the voltage level of signal, but there is only one level of power amplification, and this power amplifier enhances the power level of the signal, and finally, this RF modulated wave is fed to your transmitting antenna and is sent into space towards the receiving station. Later we will learn how receiver receives this signal and decodes it. But one interesting thing I want to clarify here, that in television there is both audio and video signal. This video signal uses amplitude modulation, whereas audio signal uses frequency modulation. So, simultaneously these two systems are incorporated there, where one is amplitude modulated, where the audio signal or sound wave is audio signal is amplitude modulated, and the video signal is frequency modulated. See, we have discussed so far how a simple transmitter section works. We have come so far that how a signal wave, may it be audio signal or a video signal, is transformed into corresponding AFSC or video FC, video AC. Then we have discussed how it get modulated. We have discussed that the audio signal is frequency modulated and the video signal is amplitude modulated. Then the voltage and power level of this modulated signal is enhanced and is sent to space or propagated through space through a transmitting antenna. Now, let us discuss this modulated wave, when radiated by this transmitting antenna, travels towards the receiving antenna by any of these three modes of propagation that we have discussed, either through a ground wave propagation, or through space wave propagation, or through your skywave propagation. And why I am not telling about satellite communication? Because satellite communication also is a type of space wave propagation in which the receiving antenna is at a very large height. Now, let us come to a simple receiver section. We will discuss now that how a simple receiver section works, what are its different components, how the RF signal is decoded in a receiving section. So, let us now see that this is a tuned circuit and this is your receiving antenna. This is your receiving antenna and this is a, I am saying this is a tuned circuit. Here you will get the advantages of modulation, because different radio stations are using different carrier frequencies. When several signals from several radio stations reaches the antenna, in the tuned circuit there is a circuit like this. This is an LC circuit with a variable capacitor. When you tune the circuit, that means you are choosing a channel, this capacitance changes. We know that the natural frequency of an LC circuit is 1 by 2 pi square root of LC, and this f value, if becomes equal to the carrier frequency of a particular radio station, that particular radio station will be tuned. That means, the carrier frequency of a particular radio station if becomes equal to the natural frequency of this LC circuit, then that radio station will be tuned. So, a tuned circuit basically it chooses the signal from a particular radio station. So, here there is your RF AC, it is fed to a tuned circuit. Now, a particular signal is chosen, this is now fed to an RF amplifier. Why? Because by travelling such a large distance, the strength of the signal is weakened. Due to that reason, this RF AC, which has got a frequency FC, is fed to an RF amplifier where the strength of the signal is enhanced. Tenu strength of RF AC is enhanced. Now, it is now fed to an IF fed to a mixer circuit. This mixer circuit has got another input from a local oscillator. So, this local oscillator feeds an RF AC of a frequency F0, and here there is RF modulated wave of a frequency Fc. This mixer circuit intermixes these two signals and creates an intermediate frequency, AC of intermediate frequency. Here I am telling AC means a signal, and the frequency of this is F prime equal to F0 minus Fc. This signal is now fed to an IF amplifier. This IF amplifier enhances the strength of this IF signal. Now, from this we can say this will be fed to a detector circuit. Now, what is a detector circuit? Detector circuit separates audio signal from the modulated wave. Audio signal from the modulated wave. Now, this is now fed to a detector circuit. This is AM wave, amplitude modulated wave. Think of that this signal is frequency modulated, then what will occur? Then it will be fed to first a discriminator circuit. A discriminator circuit. And what will this discriminator do? The discriminator converts FM wave into AM wave. So, this becomes AM wave. Remember one thing, a detector circuit cannot operate on frequency modulated wave. So, a discriminator circuit converts this amplitude frequency modulated wave to amplitude modulated wave. Now, what we are getting here? The audio frequency signal. This is now fed to a AF voltage amplifier, means a voltage amplifier suitable for audio frequency range. There are one or more stages of AF voltage amplifier, and this is now fed to a single stage of AF power amplifier, where the power level of the signal is enhanced, and finally, it is fed to a loudspeaker where the original sound is recreated. So, what is the difference between your AF voltage amplifier and AF power amplifier? AF voltage amplifier is an amplifier using class A operation, where the maximum efficiency is 35% around. But your AF power amplifier uses a class B operation, where the maximum efficiency is more than 75%. So, at power amplification level, high efficiency is required. That is why your power amplifier uses your class B operation, whereas voltage amplifier uses your class A operation. So, we can say this is how a simple receiver circuit works. So, we have discussed so far that how a transmitting section works and how a receiving section works. We have discussed that how a person speaking in front of a mic, a person singing in front in a studio gets transmitted and visualized on your screen at your home in television. Thank you.